Good evening, or good morning, good afternoon, wherever you might be. Thank you for being here. My name is Sinan Ozdemir. I am here to talk to you a little bit about getting started with open source LLMs. So, obviously, we're all very familiar with OpenAI and what they're building, although they're closed-sourced LLMs, their pricing plans, their APIs. But I want to tell you a little bit more about how we can get started with developing for open source LLMs. Now, a part of our talk tonight is going to include some history. Maybe you know it, maybe you don't. That's fine. It'll be a bit of refresher. But a little bit about myself. My name is Sinan. Yes, it is Turkish. I am the current founder of LoopGenius, where we use AI to help entrepreneurs get their first 100 customers. We are hiring a front-end dev for anyone who might want to find me or my two co-founders during networking. I also lecture for O'Reilly and Pearson. I have done so for several years before Transformers were cool to lecture about. So there's that, I suppose. I'm a former lecturer at Johns Hopkins, where I taught data science and math about 10 years ago. Went through IC, sold that. I host an AI podcast, blah, 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 blah. I write books. Let's get started. So, brief history of modern natural language processing more or less starts around 2001 with the first neural language model. This is the introduction of deep learning, popularizing deep learning into natural language processing. Fast forward about 12 years, we get the first usable, scalable word-to-vec embedding models. So if you're familiar with the term word-to-vec, maybe you're not, it was basically the state-of-the-art way to encode semantic information, raw text, into a machine-readable format before large language models. Fast forward another couple of years, the introduction of a new kind of mechanism to boost deep learning architecture starts to become popular, and it's called attention. The term attention is basically just a family of math calculations that at the time, in 2014 through 2017, was enhancing recurrent neural networks, LSTMs, to make their lives a little bit easier. But then, in 2017 comes a big shift, called Attention is All You Need. This is a paper that came out of Google, which introduced the concept of a deep learning architecture called the transformer. The transformer originally was a sequence-to-sequence model, takes in a sequence of things, let's call them tokens, let's call them text, takes in a sequence of text, and outputs a sequence of text. That's what the original transformer did. That's all it knew how to do. Now, this is the parent model for what we now know today of GPT, BERT, T5. All of these are derived from the transformer architecture. Now, I bring this up because generally you can break apart LLMs into two categories: auto-regressive language models and auto-encoding language models. You're all probably very familiar with auto-regressive language models. These are the kinds of language models whose sole job, at least in their pure form, is to predict the next token that it thinks you want it to say, given a series of past tokens. So it's like word predict. It's predicting the next word given a blank. If you don't, blank. This is how GPT works, if you can think of that. Auto-encoding models are different. Auto-encoding models have bidirectional context. They don't just have a blank at the end, they can have a blank anywhere in the sentence. So if you don't blank at the sign, you will get a ticket. With more context, what your perception of what that blank should be completely changes. Now, these are the two primary motivations for language modeling for the transformer. But when you break them up, you get this kind of, we don't talk at the family reunion kind of split, where you get auto-regressive language models like GPT, 3, 4, and all of them, frankly, where all they can really do is predict the next word in a sentence. They never have future context. They only have past context. And this is where we get the term natural language generation, which becomes generative AI. A lot of people don't like the term generative AI because it means something else in machine learning, but that's a story for another day. This is the GPT family, for example. Auto-encoding models, these are comprehensive understanding models. This is a subfield of NLP called NLU, Natural Language Understanding. And if you're familiar with the BERT model, that's where BERT comes in. BERT, which was first developed by Google in 2018, it's going to be the primary model we're going to be looking at our code. There is code, don't worry. Today, was first developed in 2018, just 1 year after the Transformer paper came out. BERT, bidirectional encoder representations from transformers, was a comprehensive natural language understanding model. It did not know how to speak, but it could listen really well, like we all should do in our day-to-day lives, maybe. Google also puts out another model 2 years later called T5, the text-to-text transfer transformer. You see where all the T's come from now, the transformer. So 2 years later, they put out T5, which is actually a pure, in the sense of there is a sequence-to-sequence, input of sequence, output of sequence. So BERT only takes in a sequence and really can't do anything about it. T5 can take in a sequence and output a sequence. Meanwhile, another company called OpenAI, a couple of months before BERT, developed GPT-1 in 2018. So GPT, the generative pre-trained transformer, again, T for transformer, is the other side of the family tree whose only job is predicting the next word in a sentence. And these companies are taking a bet. Their bets are which of these are going to become more popular and more useful. Seems like we have a winner for now, obviously, but that does not mean all other LLMs are useless. And I'm sure you're aware GPT does refer to a family of models all the way up to GPT-4 in 2023. But there have been a long line of GPT models before 4 who should get some honorable mentions. So when we use LLMs, there's generally 3 ways we use them. Again, generally. We can either encode text into semantic vectors with or without any fine-tuning. And this is often where you see examples like semantic search or some kind of retrieval problem. This is a way of using an LLM, open source or closed source, frankly, to extract that machine-readable format, kind of like Word2Vec did about 10 years ago, in a much more efficient, comprehensive, not just Word2Vec, but now it's PDF, 500-page PDF to VEC. Well, that's a little over-exaggerating, but longer-term phrases to VEC. The second way is we fine-tune an LLM that is generally already pre-trained on some data to perform a very specific task. Now, these tasks can range from the simple, today's going to be a little bit of the simple one, of sequence classification, all the way to using reinforcement learning to generate your own open source instruction following LLM. The third way is probably what you're all most comfortable with, or not all, but everybody, not just developers, is asking an LLM to just solve the problem for you without doing any developing on it. This is basically prompting. This is going to chat.openai.com or Bard, or Cohere has a new one. I actually don't know if it's public. I don't know if I say its name. But the people are making them, right? So we can prompt GPT-4 to do something. We can prompt an open source LLM like Flan T5, also made by Google, to just do the thing for us, right? So eBay, I think this was in 2000, this was a couple months ago, eBay puts out a paper, a light paper, let's say, where they use strategies 1 and 2 to completely revamp their search engine. They take a BERT model, they feed it their own data, and then use the semantic vectors that come out of it to enhance their entire search experience. So large companies are using open source LLMs for many reasons, including security reasons, cost reasons, and frankly, it's much faster and cheaper in the long run to fine-tune your own open source LLM with your data. Which brings us to how this all works, which is transfer learning. Transfer learning, blah, blah, blah math, basically just means you take a pre-trained model like BERT, GPT-2, which is open source, or T5, also open source, and these models have already seen some stuff, right? They've seen something on the internet. Original BERT was pre-trained on English Wikipedia at the time, and the book corpus, both open source, on Hugging Face. T5 was trained on Common Crawl, the first version of Common Crawl, and GPT-2 was trained on web text, which is a 40 gigabyte file of outbound links from Reddit with at least 2 karma. That's it. So I heard a chuckle. You should be chuckling, because the fact that GPT-2 was literally trained on nothing but Reddit is kind of astounding. You can read more about that in my upcoming book. So in our case, it's going to look something like this. We're going to take a pre-trained model from an open source repository, Hugging Face in this case. We are going to take that pre-trained model. We are going to add a task layer on top of it to perform the task that we want. Because again, BERT doesn't know how to speak. It's a really good listener. So we have to give it a bit of a mouth to do the thing that we want it to do. And then we're going to feed it some data. We're going to use an open source data set just so we can all follow along. I'm not going to use a proprietary data set that only I have access to. That wouldn't be fair. And that data set is coming from the GLUE super corpus. And the specific task is called QNLI, the Question Natural Language Inference Task. Basically, it takes in two pieces of text, a question and a passage. And the task is simple. Does the passage have information that would answer the question? I don't care what it is. It doesn't matter what the answer is. Is this a passage that would answer the question? And you can think of this in day-to-day life as, well, I would want to retrieve information from a textbook and make sure that this information will answer the question if I'm making like a tutor AI. So this QNLI is a really basic and powerful task that can be expanded to all kinds of industries. So what our kind of low-level model is going to look like is something like this. If you've never really seen the inner workings of BERT, don't worry about it. But the basic premise is BERT takes in a tokenized sequence of words, tokens, I should be more clear, and also with reserved tokens. So CLS is a reserved token in BERT, stands for classifier, and also the SEP token, which stands for separator. All LLMs have reserved tokens, even GPT-4. They just hide it on the back end, which is fine. All LLMs have reserved tokens. That's probably not true. I'm sure someone made one without a reserved token, but pretty much any modern popular LLM will have some reserved tokens. And what we're going to do is we're going to add this layer on top of CLS with basically just a simple feed-forward neural net layer that you would find in any PyTorch implementation before transformers. And it's just going to classify between 0 or 1. And the labels here are entailment and not entailment, which is philosophy speak for yes or no. Yes or no, is this passage going to answer the question? Entailment is yes, not entailment is no. So the reason I'm doing this example today is because if you don't know anything about BERT, you may also not know that BERT is something called a cross-encoder. What does that mean? A cross-encoder is a kind of large language model. Unlike GPT-4, no GPT model can do this. It has been pre-trained to specifically take in two sentences and perform a task in parallel with full context on those two pieces of text. Now, you may be asking, well, I could just put two pieces of text in GPT-4 and it's the same thing. Not exactly, because when you put two pieces of text in GPT-4, it only can read left to right. So if you put one text first versus the other text first, it actually will be unaware of the second text that you put afterwards. GPT-4 cannot read ahead of itself, even on the prompts that you give it. When you type something in, the first word is not yet aware of the seventh word, even on the word that you type in. But BERT breaks that. The B in BERT is bidirectional. It is aware of all tokens all the time, always, which makes it a better listener than GPT-4 and a faster listener at that. So we're going to be taking advantage of the fact that BERT is able to take in two pieces of text once and process them extremely quickly. In our case, the two pieces of text are the question and the passage. So when we get to our code in just a minute, I'm going to be walking through a bunch of tips and tricks on how to fine-tune open source LLMs fast, quickly, memory efficiently, without sacrificing performance. And one of the many tasks, or I should say, one of the many characteristics I'll show you is called freezing. You may be aware of this. It's basically the premise of, well, BERT has a number of parameters. BERT base has about 110 million parameters. Small by modern standards, but nothing to sneeze at. Bless you, by the way. But so what you basically will do, vanilla training would look like you take the BERT model, you add the classifier on top of it, which is like 1,000 more parameters out of the 110 million. And you say, great, I'm about to show you thousands of data points, and I want you to effectively unlearn on everything you've learned, or at the very least, use it, transfer it to this new task. But if you have information that is not relevant to this new task, you're probably going to have to sacrifice it in in order to learn this new task. This is what you get with smaller parameter models. Now, freezing comes in if you say, well, I want to speed up this process, and I also don't want BERT to unlearn a lot of stuff. So what often people will do is say, well, if BERT has 6 encoders, an encoder is just a level of attention, basically. If a BERT model has 6 encoders, you could say, well, I want to freeze the first 4, i.e. they're not allowed to update. They're not allowed to unlearn, relearn anything. Only the final 2 encoders and that classifier that we added on top, because it hasn't learned anything yet. It was completely randomly initialized. This will be a faster training session, but you'll usually get a hit on performance. The extreme of this is to freeze all in BERT. You can never freeze the classifier. Again, the classifier is randomly initialized. It has to learn something. But if you freeze everything else, you'll get the fastest performance, but fastest training time, but generally the worst performance. This a second thing that we'll see in our code is dynamic padding. And if you're kind of worried about how much code there is going to be, then one of the nice things is Hugging Face has effectively built all of this in to their transformers package. So we're going to be using almost entirely the transformers package to do all of this. We are barely going to write any code by hand. We're going to be using almost all of transformers pre-built packages. One thing they offer is called dynamic padding. If you've ever done machine learning before or fine-tuned a model before, when you have vectors of text, they all have to be the same length when they enter the model. Now, the naive way of doing this would be to say, well, I have all these pieces of text of varying length. I'm just going to go ahead and pad them all to the largest one before I even start my training, which is totally fine. You're allowed to do that. But it's very inefficient because if your longest text is like an outlier large, you're leaving money on the table, and that's not good. So what dynamic padding will do is say, well, don't pad it yet, but every time you take a batch of data, like 8 of them, 32 of them, 64 of them, every time you take a batch of data, pad that to the largest element in that batch and that batch alone. So you end up with a batch size on average much smaller, which, as you'll see, leads to much faster training times. So let's go ahead and switch to our notebook. I'm going to go ahead and do that right now. And if you do want to follow along, I do have a GitHub for this. So all the notebooks I have are on that GitHub. So if you do want to follow along now or read it later, I would love that. So on this repository right here, Sinan Ozdemir, AI user group, I'll leave it on the screen for as long as I can. We have 2 notebooks. The first notebook, the primary notebook, is called Fine-Tuning BERT. And if you've ever taken a class with me, you know that I always have extra material. We probably won't get to the T5 notebook. By design, it was there just in case I had more time and wanted to do it. So let's go ahead and do this. Now, I'm going to go ahead and go right out. Hugging Face has a much more comprehensive version of what I'm about to tell you. They're much more focused on GPU memory optimization, which still transfers over to your laptop CPU. But if you want a really in-depth version of this, Hugging Face has it. Here's a little bit of a shorter version with the easiest things that you could all go home and do tonight. So our imports are actually quite small. We're only importing 2 things, both of them from Hugging Face. Datasets, which is a Hugging Face package, and transformers. And from transformers, we're going to import 5 things. A trainer, which will do our training loop. Training arguments, which is just a class to hold the arguments for training. A data collator with padding. This is the thing that does dynamic padding. An auto model for sequence classification, which is the generic class for a model with a classifier head on top to perform some sequence classification, and a tokenizer, a thing that will break down text into tokens. So here's a function that's just going to create a BERT model. So just so I can create a BERT model whenever I want. And the main model we're going to use today is BERT base uncased, the OG BERT from 2018. So one of the oldest LLMs in existence. We are still going to make it do a modern task for us with data. This function just creates the model. It's going to return an auto model for sequence classification. I am going to kind of hard code in the labels that I know what the labels are. There's only 2, entailment, not entailment. And if you call that function, get blank model, you just get a BERT model. It has 12 encoders. The BERT base has 12 encoders. And at the end, it automatically adds on this classifier, which outputs 2 features, 2 because entailment, not entailment, yes, no. Cool. our data, as we mentioned, is the QNLI data set. And to load data, actually I don't need this. I already did that up there. To load the data, all you have to do is called load data set, give it the name of the data set, which if you are on Hugging Face here, they will give you code on how to do that. If you ever want to, I don't want that. Doesn't matter. I did it here for you. So here's how you would load that data set, which I copy and pasted from Hugging Face. I'm also going to take a sample. It's a large data set, but just for the sake of kind of running this on our laptops and not that long a time, but still showing a delta in performance and time, I'm only going to take the first 1,000 elements in the training set and 200 in the validation set. That's it. Now, I also do a quick filter to remove any negative ones. There weren't any, but it's good habit. If you know there are missing data, just remove them. Assert that we have data. This is just backend, me kicking in and making sure I have asserts there to make sure everything is fine. And then we're going to do our first real open source learning. We're going to take our raw data, which I'll show you, looks something like this. This is all our raw data is a question. When did the third Digimon series begin? A passage, which is a passage about Digimon, one that does not answer the question, but it's about Digimon. And the label 1, which if we go back to the data set, is not entailment. So this passage does not answer the question. Third season was dark. I'm not going to lie to you. Third season was weird. I didn't like it. But I grew up on Digimon. That's just me. Now, so that's our raw data set. So what we're going to do is we're going to run our tokenizer, our thing that converts text into tokens, across all of these with no padding. We're not going to do any padding. Sorry, I should rephrase. We're going to start by doing the padding, all of them up front. So we're going to do the thing that I was saying not to do, just to see how bad it is, which is here. We are on the top right. We are going to make it pad all of them to the max amount. So it's not going to go well, but we'll see. And we're done for our training and our testing set. And then it will look something like this. We solve our question and sentence, which for being ultra optimizing, you would remove that because you don't technically need it anymore, but just to show you what it looks like. We have our label 1, which is not entailment, bad. Then we have input IDs, which is the token ID. So all of these numbers correspond to vocabulary items in BERT. 101, because I use BERT so much, is the CLS token. The CLS token is always at the front of any BERT tokenization. And if I go here, 102 is that SEP token. That SEP token is a reserved token that says the first text has ended, the second text is about to begin. So again, it is aware of the fact that it can be given 2 sentences at once with full context, front and back, bidirectional encoder representations from transformers. And then that's all we really need. There is other stuff at outputs, token type IDs. This just tells me which one is sentence 1 and which one is sentence 2, zeros and ones. And something called an attention mask, which is, long story short, a way to tell it this has been padded or not padded, i.e. this is relevant information or not relevant information. If attention mask is 1, it's relevant. If it's 0, it's a padding token. Pay no attention, pun intended. Do not calculate attention for that token. It is a pad. So then the last thing I'm going to do, just to make our metrics a little bit nicer, because I'll tell you right now, the trainer object in Hugging Face, the only metric it's going to give you outside of time and how long it takes is the loss that you can also set, which obviously we want. We want the loss function. We want loss to go down. Loss going down is good. But just to kind of make it a little more, human readable, I'm also going to calculate accuracy, precision, recall, and the F1 score on the testing set. So we're back to just machine learning. I have a training set and I have a testing set. The only difference is the model happens to be a large language model. At this point, it's no different. So I'm also going to save all these metrics for a graph at the end here. Now, the default arguments are going to be, you can give it a folder on where you want to put the files. I have how I want to evaluate on epochs. 1 epoch, which means I'm only going to read the training data once, a batch size of 32, and an eval batch size of 32. By the way, I'm going to go a little bit over. Is that okay? I'm looking at you. Excellent. Thank you. He's entranced. The BERT, I know. So I'm going to make a blank model. again, a randomly initialized classifier layer, but a fully pre-trained on Wikipedia and book corpus, BERT. I'm going to instantiate my training arguments, which again is just a class that holds arguments. It's a dictionary effectively. And then I'm going to define my trainer object, which will take in the model I'm going to train, the training data set, the testing data set to perform my validation metrics on, the tokenizer that it's going to use, the arguments that I just defined up here, and an optional compute metrics. If you don't pass this, it's just going to give you loss. If you pass my compute metrics, it will give you accuracy, precision, recall, and F1. Trainer.evaluate will give you my initial metrics, initial accuracy before doing any training, which is going to suck, obviously, but just to show the delta on how well it does. And then we run a train, which runs the one epoch of data. We'll evaluate again, and then I'm going to store these metrics in my dictionary. So just on this first one, and again, this is totally vanilla training. It's the bad kind of padding. It's a batch size of 32. That number will come up again. But it's just vanilla training BERT. If you basically asked GPT-4 to write code to fine-tune BERT, it would give you something like this. It's not wrong, but it's not optimal. Now, the initial loss of 0.68 dropped to 0.58. Fine, it's only 1,000 data points, again, so it's not amazing. And our accuracy rose from 0.5 to almost 70%. So it's learning. Even on the 1,000 data points, it's learning QNLI. And if we gave it the tens of thousands or hundreds of thousands of data points, it will learn more. But it's learning. That's all we need to know for now. First trick. If memory is a problem, this is not just a speed boost, it is much more a memory boost. If memory is a problem, i.e. your model doesn't fit in your RAM, specifically because your batch size is too big, easiest thing you can do is to drop the batch size from 32 to 8 in this example, and add gradient accumulation, which is math language for before you do your backpropagation and gradient descent, wait 4 turns of seeing 8 data points, which creates an effective batch size of 32. So it doesn't perform the main crux of deep learning, backpropagation and gradient descent, until it has seen and accumulated gradients for 4 batches of 8 data points each, making an effective batch size of 32. Now, I'm going to skip the metrics for now because I want to show you them in the end as a graph, but that's the first trick. That's going to save you not just time on a CPU, but massive amounts of memory on a GPU. It is the number one easiest way to save memory if you're training, even on a single GPU on Colab or if you have one at home. I have one at home on a computer I affectionately call Kronk, from Emperor's New Groove, because he is a himbo. He's strong and dumb and stupid, but I love him. So dynamic padding is the next one that I talked about. So again, instead of padding all of them to the same size up front, I'm going to do it dynamically for each batch. And I'm going to do the same thing. The difference now is, if you remember, I imported data collator with padding. I haven't used it yet. Now I'm going to use the data collator with padding. If I don't do this, transformers on PyTorch will use the standard data collator, which does literally nothing. It just takes the data, puts it in batches, and shoves it into BERT. No padding, nothing. This one will perform the padding before giving it to BERT, which is what we want. So we want to dynamically pad our data. The other thing we need to do is our training set. Remember, we padded it to the maximum length. I'm going to redo that. This is a new training set, so I have to redo my tokenization without padding this time. Now, in my real life, I would have done it in the first place. But this is how you should be padding your data in your day-to-day life. You should be padding it, or you should be tokenizing it without padding and reserve the padding for training time. Again, everything else is the same. You got a model, arguments, trainer. Only new thing here is I'm passing an optional collator object, evaluate, train, blah, 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 blah. So this one now has the gradient accumulation and dynamic padding. And I'm going to give you a little bit of a sneak peek and say, our timing has gone down significantly. The first amount of time it took for the vanilla training, I believe this is the vanilla training, yep, was almost 2 minutes. I know, staggering. We've already gotten it down to 1:28. Now, that might not seem like a lot of seconds, but if you're thinking hours, we have now just seen a drop in 25% of time, and we have done almost nothing, and accuracy is actually a little bit better. That's a little bit of that's going to be more or less. This is not supposed to improve your accuracy, but it's maintaining accuracy at 25% training speeds and a much significant memory bonus if you're doing it on a GPU. Model freezing. Now I'm going to instantiate a blank model. And now, before I feed the model in, I'm going to iterate over the parameters. This is a little bit of a hacky way. They don't have an easy way to do this in transformers, but the easiest way to do it would be to iterate over the named parameters. So like the encoder parameters, the attention calculations, like if you're familiar with attention, query, key value transformations, a lot of linear algebra. It's a lot of fun. I used to teach it at Hopkins, so I love linear algebra. So what I'm going to do is, because I know it has 12 encoders, I'm going to freeze everything until it hits the 6th encoder index, Python index 6. So 0, 1, 2, 3, 4, 5, and also the word embeddings are all frozen. And the way you freeze a parameter is by setting the requires grad attribute gradient to false. That will completely halt all gradient accumulation. So it will never update. So I've frozen more than half of the model. Everything else is now the same. Training arguments, trainer, compute metrics, everything. And now I have a new model with not as good accuracy. Now, if we were to visualize our performance here, it would look something like this. So our vanilla training here on the left has an accuracy of about 70%, if you recall, on this blue, on the blue with the hatches and with the stripes here. Which, by the way, I did have GPT generate the code to make this graph. And if you want a tip on how to make graphs that are easy to read for audiences, ask it to make it more accessible for the visually impaired. It's going to add a lot of contrast. It's going to add a lot of patterns. It's a really nice prompt to make your graphs a little bit nicer. So as you see, as we keep adding our tricks, our accuracy actually maintains for our gradient accumulation and dynamic padding. But we see a big drop in training time. Training time has gone down by about 30% at this point. And our loss functions, our loss values rather stay around the same. The only time this is not true is our freezing, and this is expected from our slides. The more you freeze, the more likely you're going to get worse performance. But as you can see, it is almost half of the time to train, and you do take, again, from 70 to about 62% accuracy, which is now a common task of, is it worth it? Is it worth half of the training time for 8% reduction in accuracy? I don't know your life, and I don't know your choices. It might be. If you need to train your model every day, and if your customer support, your CSAT doesn't really take a hit if your accuracy drops 8%, go for it. Why not? But this is something you're going to experiment with. You're going to experiment with how much should I freeze? There's obviously way more advanced techniques like gradual unfreezing. You freeze everything, and every epoch you unfreeze a little bit of the model to kind of get the best of both worlds. And then to use our model, it's very simple. We can import from transformers a pipeline object. The pipeline object takes in our fine-tuned model, which we will generate, or rather load, from that directory that we set. And this is, by the way, the one with gradient accumulation and dynamic padding, which technically have the best performance and a good training time. And then you can just pass in pieces of text, open source, in your notebook. And this is correct, by the way. The first ones are entailed. The second two are not entailed. Easy peasy. So coming back to our slides, just to kind of wrap things up, because I know I want to stay a little bit on time here. Size isn't everything. The model we just used was 110 million parameters, but with enough data and with proper training techniques, you will make it outperform GPT-4 on hyper-specific industry-related domains. If you want to check out my new book, I have several examples of doing that, beating GPT-4 handily, just by feeding it data in an appropriate and efficient manner. You can beat GPT 3.5 and 4 on several tasks. Will you beat it on every task? No. GPT-4 can solve thousands of tasks, but most of us don't need to solve thousands of tasks. We need to solve like 6. So if you need to solve like 6 problems, look for an open source model to solve those 6 problems. If you want to check out my new book, I do go beyond this with reinforcement learning and kind of showing those like more optimal techniques on how to use reinforcement learning to do your fine tuning. Here was an example of taking a FLAN T5 model, making it more neutral, making it a bit less opinionated, more factual, more neutral. Here's an example of me trying to make my own instruction fine-tuned model from GPT-2, the open source 110 million parameter GPT model from OpenAI, where I can actually actually will be able to answer questions that you give it, like rewriting sentences to have a different feel, or writing a mythical backstory for my D&D character of Daedric, Prince of Solitude. So you can make these open source LLMs do some pretty cool stuff if you just pay attention to how you train it and how effectively you can pass those data into those models. Now, I'm going to end it there. I will say the one thing I will say before I go, on the GitHub, I do have an example of using that model to make a Streamlit app. Streamlit is a really lightweight way to kind of share and prototype your models. I have it online on Hugging Face, but all that's in the GitHub as well. But I'm going to leave you with, I hope this pretty short discussion gives you some new perspective on LLMs. When it comes to size of data, I promise it is not as important as quality of data. I promise you, more data is almost never the answer to your problems. I would say the right answer to that question would fall more in line on, are you mining data? That is your training data as close as possible to your inference environment? Now that might sound easy, but oftentimes we'll get this. Well, hey Sinan, I listened to your talk and I took that data set with Digimon in it and I used it and now I'm deploying it for my IT company. It's not going to work that well because the QNLI data set does not have a lot of IT information. So it's going to be really good at understanding animes, but it's not going to be super good at understanding, I dug myself into a hole here, something smart IT related. So it's a mismatch. And just because it's the same task doesn't mean the data makes sense. So the data is going to be close to your environment as possible. Now, again, back to size, as long as you have a proper split of data, training, testing, validation, and there are 3 splits, not 2, training, testing, and validation, as long as you're performing those splits appropriately, you're using 2 of them to do your fine tuning and reserving a totally set apart data set for final evaluation, that final evaluation should have enough data for everyone to be comfortable deploying that model. Now, if you want a number, I'll give you a number. If you're thinking about putting a model in production, I would bat an eye if you told me your testing set was under 1,000 data points. I would be like, oh, interesting. Like, why do you not, is there no more? Could you get a little bit more? Similarly for training set, about 10,000. That doesn't mean you need 10,000 data points to get a production-ready model. Not true. But I would start to wonder, could you not get more, or what's the reasoning there? There were some chuckles when I said OpenAI use Reddit to train GPT-2. I don't like that. That's not good. Have you ever been on Reddit? Some people on Reddit are not the most truthful. I know. And it's a reason why I use GPT-2 to make my own instruction fine-tuned model. It becomes, I don't want to spoil it, it becomes obvious pretty quickly where it learned its information from. So I'll leave it at that. Make sure your data source is safe, is ethical, as non-biased as you can possibly get it. Humans are biased. It's close to your inference environment, and let's say 1,000 for training, or 10,000 for training, 1,000 for testing. Fair? Fair.